Okay, we're going to start chapter 13. Before we do that, we're just going to quickly finish up a couple of the exercises we left from 12.6. So here, notice that the max value z can take is 8. Because say, for example, if z was like 10, then you'd end up with, say, 2 being negative x squared minus y squared, which is not possible. So what ends up happening is, so for 1 here, at z equals 8, you end up with x and y being 0. If z equals, say, 4, then you end up with the equation x squared plus y squared is equal to 4, which is a circle of radius 2. Let's say z equals 0, you get another circle. X squared plus y squared is equal to 8. And so what happens is you have this downward pointing, so there's at 8 here, there's a point, and then there's a circle, and then a slightly bigger circle. And if you set, say, x to be 0, you're going to get a parabola pointing downward, and so you get this paraboloid, downward pointing paraboloid. So this is a downward paraboloid for 1. For 2, as I suggested, with switching everything to the other side, you get z squared minus x squared minus y squared is equal to positive 3. And so, for example, z cannot be between, strictly speaking, negative 3 and 3. So, for example, if z was 0, you have negative x squared minus y squared being 3, and that's not possible. At 3, you get x squared plus y squared equals 0, so that means that x and y have to be 0. If you have plus or minus 4, you get x squared plus y squared is equal to 1, which is a circle. And so here is 1, and the z, here's 0, 0, 1, here's, I'm sorry, 0, 0, 3, 0, 0, minus 3. And then you have circles above those at 4, at negative 4, and so on. And if you set, say, x to be 0, you get z squared minus y squared being 3. That's a hyperbola pointing up and down in the z direction. So you get these hyperbolic shapes. And so you get the hyperboloid of 2 sheets. And how do you know that it's 2 sheets sort of off the bat? If you have a 1 positive term here and 2 negative terms, and then a positive constant. So positive constant, the 1 positive square term, 2 negative square terms. That's indicative of the hyperboloid of 2 sheets. On the other hand, if you had, just FYI, if you had a positive constant, if you had 2 positive square terms and 1 negative, then that would be your 1 sheet. Okay, so that's from last time. And that concludes, that's the end of 12.6. 13.1, so chapter 13 is all about vector valued functions. So what is the definition of a vector valued function? We've already seen it a little bit without defining it separately, but so a vector valued function is of the form. So we have a map R that takes a real variable t to some x of t, y of t, z of t, or more abstractly, it takes the real line and bends the real line in R3. So essentially, R of t then is, well, first of all, it's equal to x of t, y of t, z of t. But it's a curve in space. It's a curve in space. So it's, if here is your three-dimensional space, then R of t will, something like this. And it's directed in time. It has a direction. So as this arrow indicates t going to positive infinity. So moving forward in time. Okay. So just before we jump into some examples, just a couple of things to note. So the limits, how do you define a limit? Well, you define it just like you do in single variable calculus. If you want limit as t goes to t naught of r of t, it just goes in piecewise. The limit t goes to t0 of x of t, limit t goes to t0 of y of t, and the same thing for z of t. So the limit concept exists in the same way, essentially by component. And so using the limit concept, you can define continuity also. So R of t is continuous at some t naught if the limit as t goes to t naught of R of t is equal to R of t naught. So this is the definition of continuity, and it's just the analog of continuity in single variable calculus. Similarly, you can define the derivative. So differentiability. So I'll just put it this way. R prime of t naught, what is this? This is the limit as h goes to 0 of R of t plus h, t naught plus h minus R of t naught over h, and where the limit, all of this is defined using the fact that the limit goes into each component. And so hence, because of this definition, I know I'm going through this a little rapidly, guys, but you just extend everything and do everything component-wise. So hence, R of t is differentiable at t naught if and only if all of its components are differentiable at t naught. Okay, so that's the idea of differentiability in abstract. In practice, it's just take the derivative of each component. So, but before we jump into all that, let's just do some basic examples of some curves. So examples of curves, and we'll come back to the whole differentiable stuff a little bit later. But I just wanted to mention that because it's important to note. Okay, so let's do examples of curves first in R2. So for example, let R of t be t squared comma t. And what we want to do is we want to graph this, and we want to indicate what's called the orientation. And that's basically given by the arrow sign, indicating in which direction as time goes forward is the curve going. Okay, you can think of like a particle, and the particle would flow in the direction of the arrow. So here we have x of t being t squared. We have y of t being t. So x is y squared. Based off of this, we can conclude that, well, this is just the equation x equals y squared. And hence the graph is just the x equals y squared graph. Now the question is, how does the arrow point? Well, when t is at 0, we're at 0, 0. When t is 1, we are at the point 1, 1. So we're going in this direction. Okay. So this is an example of a curve. Let's do another example here. R of t is 2 cosine t, 2 sine t. Note that this, you probably have seen this parameterization at some point, maybe when you did polar coordinates or something like that. Note that here x squared plus y squared is equal to 4, and hence this curve corresponds exactly to the circle of radius 2, centered at the origin. The question is, how does this oriented? Well, at t equals 0, we're at the point 2, 0. If you plug in, say, pi halves, you'll get the point 0, 2. So we're oriented counterclockwise, which is our standard usual trigonometric orientation. How would you reverse the orientation? So the one question that arises here is how to reverse orientation. And there are times where you want orientation. How would you reverse the orientation? Sometimes it ends up being important. Probably if you do vector calculus, you'll probably see some examples of that. But essentially, if you replace t with minus t, let's see what happens. So if you have cosine of minus t to sine of minus t, and we know by the properties of cosine and sine that this is actually just 2 cosine of t, because cosine is even, and this is negative 2 cosine of t because sine is odd. And hence, so for example, it's the same circle, but at t equals 0, we're at 2, 0. At t equals pi halves, we're at 0, negative 2. So this actually, the circle is the same, but we start here and we're moving in this direction in positive time, so hence this is actually clockwise oriented. And this is always going to be the case. If you switch t to minus t, so t to minus t replacement reverses the orientation. Okay, let's do an example in R3. So R of t is 2 cosine t, 3 sine t, and say 5. So this is almost, well, let's start with something simple here. Note that whatever this curve is, it must lie on the plane z equals 5. So this is a curve in the plane z equals 5, because z equals 5 is a constant. On the other hand, we have 2 cosine t, 3 sine t. Notice that if you do x squared over 4 plus y squared over 9, this is equal to 2 cosine t squared over 4 plus 3 sine t squared over 9. This is equal to cosine squared plus sine squared, which equals 1. And so this curve actually corresponds to the equation x squared over 4 plus y squared over 9 is equal to 1, which is an elliptical equation. So we simply have in the plane z equals 5, so here is 5, can draw the plane, then we have an ellipse that would be defined by that equation. So essentially, let me get rid of this plane because that's technically not part of the graph. We have the ellipse sitting in the plane, z equals 5. Which way is this oriented? That's the last part of this. 2 cosine t, 3 sine t. Well, if we plug in t equals 0, we would be at the point 2, 0, 5, which is right here. If you plug in, say, t equals pi halves, we would be at 0, 3, 5, which is right here, and hence we're oriented this way. Okay. Okay, so those are some examples of curves. Let me give you an exercise here to try, which is, all right. So to graph and orient the following. So this one will be r of t equals t, and t squared. Okay. And do the best you can with these. B would be r of t is equal to cosine t, sine t, and t. Okay, so we'll stop here for now, and we'll continue with those exercises in the beginning of the next video.